Hello and welcome everyone. Thank you for joining us today for our webinar titled More Use Cases and More Value with Automated Computer Vision Modeling. My name is Patrick Moran. I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speakers. Dan Darnell is VP of Product Marketing at H2O.ai, and Eugene Babakin is a Kaggle Competitions Grandmaster and Data Scientist at H2O.ai. Now before I hand it over to Dan, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. Now without further ado, I'd like to hand it over to Dan.
Thanks, Patrick. Great to have everybody join us today to talk about this great topic. Really excited about the Driverless AI 1.9 release. We did an overview webinar last week. If you haven't seen that, please go to our website and watch the recording. And we're doing a number of other webinars on various topics, including NLP and explainability in the coming weeks. So keep eyes out for those. So today's topic, we're really going to go through some very basic overview of computer vision. We'll talk a little bit about what we're releasing as part of the 1.9 capabilities and our roadmap going forward for computer vision use cases. Eugene's has graced us with his presence to do a demo, considering that he's a grandmaster for both machine learning and deep learning competitions. Really excited to have him here. He'll do a demo and overview, and then we're both here to answer some questions in this fairly short time that we have together. So computer vision can be broken out into a number of different problems. The first set of problems, and the ones we've solved first in our roadmap, is really around classification and regression in images. And we're working on some of these others. You can imagine, as you look through these different areas, the different kinds of use cases you could solve with each one of these. With kind of classification and regression, there are a number of common use cases across industries that people tend to talk about. If you look through the literature and see what people are doing with computer vision, or what's sometimes known as visual AI, you'll find things like in healthcare, they're doing like image classification around X-ray images or thermal images or MRIs to try and help physicians, find patients that have conditions that need further treatment. In manufacturing, one of the common use cases that I have personally talked to people about, and that you hear about across a variety of industries, from semiconductors to jewelry, is just using images to find defects in the manufacturing process. And that's a really interesting one, because it means you kind of have to put the models out into the manufacturing environment, sometimes on the machines themselves, and use them in the moment kind of to do that quality inspection based on the image of a circuit board or a piece of jewelry or whatever that might be. The next one is retail. Maybe some of the creepier use cases have to do with kind of watching people do things and, recognizing people in context. In retail, some of the more interesting ones are like, as shoppers come into a store, kind of determining their gender, or maybe using the system to understand what areas of the store people were most interested in, or what their intent was based on kind of how they were oriented in the store, what they looked at, things like that. You can also use kind of visual image processing by taking pictures of the inventory over time. You can actually figure out what portions of the inventory need to be updated, right? So instead of having someone go out on the shelves and figure out what portions of the shelves need to be, replenished, you can use cameras for that now, and then you literally just have an order show up back in the warehouse that says, hey, we need to bring more of this kind of product out to the floor. For insurance, one of the common use cases is better pricing claims. So a lot of times with let's say a car accident claim or a house accident claim, you'll have images that go along with that to show the tree that fell on the car, or the car that crashed into the other car. Well, you can now use those images to help process the claim, not just what an assessor wrote, or not just what the individual wrote about the accident. But you can also use the images of the car, if you think about it, to assess the value of that potential car. Like the person might say, the condition of my car is amazing, it's great, but through the images you can actually assess that the car's is only fair in terms of its valuation, right? So there's lots you could do in the insurance sector. And then one of the surprising ones that people might not know about is how much this is used in agriculture. If you have drones, for example, flying over fields and taking pictures regularly, you can actually do things like understand where you need to apply, weed control by recognizing weeds compared to your crops. You can check for soil quality issues, like where you may need to apply fertilizer or other things, as well as watering needs, right? So instead of just watering everywhere all the time, you could actually be more selective about where you apply water. And you can automate a lot of those processes by looking at the images of the fields. Another one is just sorting produce. This is actually being used today where the produce comes in, much like the kind of defect detection in manufacturing, the images of the produce are actually used to kind of sort it. So, if this peach looks like it's good and whole, it can get pushed over into the good produce line. And if it looks like it might be damaged, it can get pushed over to a human to do an additional assessment, or it can get pushed over to a secondhand, fruit selection and then be sold that way. So lots of amazing use cases for this technology on its own, as well as adding image data to other data sets. So just for those who are not familiar with our product, Driverless AI, which is a automatic machine learning platform, and now deep learning as well with the addition of this type of model, this platform automates the full process of creating models and outputs a scoring pipeline that can be used in production. And so what you do is you bring the data in this case, image data or a file that includes images, and we'll actually process that data, get it ready through the feature engineering process, the encoding process, run a number of different models, and then compare those models, and then output the best one so that you can put it into production. And that's the process that we'll show you in the demo, but for image-based models and models that include images. So in terms of how do you bring in the data into the system, you can have a file. So you could have a traditional data set that you would use in the system today with a variety of features in that data set. And some of those columns can now be images. Or you can bring in the images in other ways. You can just import an archive of images. And if that archive, as you see in the example here, contains some classification, like this training data, normal and pneumonia, the system will infer the classes from that structure, which you brought into the archive. But you can also, as Eugene's going to show, you'll also see that you can use files like CSV files and other files that can point to the data that might be stored locally or even stored online, like URLs to images, things like that. In terms of the approaches, a couple of different things are going on here. We talked about the situation where you're going to include image data in a file with other data that you might have. And a great example of that would be that insurance claims use case. In that case, I'm going to have other information about the insurance claim, maybe from an adjuster or from the customer, about the model year of their car, what happened in the accident, how much damage they're seeing, where they're seeing the damage. In that case, I probably want to convert the images over, and I would use an embeddings transformer to convert images over to fixed embeddings as part of that file, and I could run that on CPUs, just like other traditional models. And I can use models that I might be more familiar with, like tree-based models, GLMs, things like that. On the image classification side, you're using images only. And so that archive we just showed with the images, which are normal and pneumonia, you're just bringing in the image only data, and that you can use GPU acceleration. We would recommend that because it'll take a while to process without it. And then you can build models just with the images alone. Now, one of the things that's interesting about automating this process is if you're a data scientist who is trying to solve problems around images, you might be forced to use the technique that you're most familiar with, right? What we can do because of automation is we can look across all the various available architectures and techniques and these pre-trained models, and we can actually bring a bunch of those into the system and allow you to build models with all of them if you want. And if you're an experienced data scientist and you know exactly what you want to use, you can select that one and use that. But a number of advantages to automating this, and running it on top of GPUs is you could test a bunch of things you may not have been able to test. And some of those techniques or pre-trained models may actually be better than what you're familiar with, right? So one key advantage of automating this process. So what does it look like and what you'll see in the demo? Like after we run the model, you're gonna wanna understand what happened potentially. And here you've got a bunch of really cool visual ways of doing that. You can see, for example, you'll see that in the middle there, what portion of the image was used to determine, in this case, that it was a mouse. You can see the red area. It says, well, I kind of looked at its face here and determined that it was a mouse. But you also get places where the model, you're going to have some kind of errors in the model. It's not going to be 100% accurate. And you get to see where the classification, for example, failed. Well, hey, this is a mouse, but I predicted it was a dog, right? Maybe because of the way this image is set up and the mouse is kind of cut in half and it's very small or something like that. And so you'd have the ability to kind of go through and look at positives and negatives and better understand how the model is classifying. As well, the processing is going to augment and potentially change images. It's going to show you augmentation of those images so you understand how it used those images in the training process, right? So a bunch of different really visual things you can do here after you've built a model to understand how the model works, right? And to just check it as a data scientist. And of course, at the end, this pipeline is, we vectorize the images as part of our larger model, and we put that into a scoring pipeline. So just like other types of models you have in driverless AI, you get a low latency scoring pipeline, which you can then take and deploy out into production to provide, in this case, classification on various images. So super easy to use, super easy to deploy. In terms of roadmap, a number of things are already done or are in progress. What we're releasing is, as I said before, classification and regression in the release 1.9, and continuing to work on semantic segmentation, and then these other areas of object detection and instance segmentation we expect to come out later this year. So with that, I am actually going to stop sharing, and Eugene's going to start sharing his screen.
Yes, thank you, Dan. Probably not stopped sharing yet. Okay. Okay, could you see my screen?
Yeah, I see it.
Yeah, okay. So yeah, I'll briefly start with the data sets, with what data format we expect for the images, and then has already described it a bit. So what we have here in Driverless is this dataset tab where you're uploading your data. And basically for the images, you have multiple ways to upload it. The first way is this directory structure. We have the directory of your images on the disk. For example, this just express datasets from Kaggle, where we have two directories, normal and pneumonia. And you just zip these two directories into a single file and upload it to Driverless. And it will automatically create such a file with the image column. It will be a physical pass on the disk, and also a label. In this case, it is just binary, normal, or pneumonia. Another opportunity is to provide their physical passes on the disk. It means that instead of uploading the zip file to their Driverless, you're just uploading the CSV file where you're providing the physical pass on the disk. So you don't have to provide, if you have like millions of images, you don't have to upload everything to the Driverless. You could just provide the links as a direct links on the disk. And the third opportunity is remote URLs. So if you store your images somewhere in the cloud or just in the internet, then you could just provide their image URL. And Driverless will also use these image URLs for modeling. So I will start with one of the datasets. It is also from Kaggle, from one of the past Kaggle competitions, from the pet finder. The idea here is that we need to predict the time range when the pet will be adopted from the shelter. And we have different parameters of the pets in the shelters, so including the image and all others like age, gender, size, and so on. And so driverless could handle this dataset altogether. So we could model altogether tabular data, text data, images. So all you have to do is click predict and create the experiment. Here we have 15,000 of rows and 7 columns. So it is the subset of this pet finder dataset. We're selecting the target column. In this case, it is adoption speed. So it has 5 unique values from 0 to 4. It just splits the time range into five bins. And in the expert settings, we have a special tab called image. So basically, you don't have to change anything. So by default, you could just start the experiment and everything will work out of the box. However, if you want to somehow customize the available hyperparameters, you could go here. And for example, you could select from the list of the available pre-trained models. So here we have different families. So you could select multiple ones. And in this case, the image will be transformed multiple times with different transformers. And also we have an opportunity for the fine-tuning. So the idea here is that we will fine-tune our model for a couple of epochs on the dataset provided. And in this case, instead of getting their embedding vector from their ImageNet pre-trained models, we will obtain the embedding vector, the vector representation of the image on the dataset, on your dataset. So it means that the quality of the embeddings should be better. This option requires a bit more of computational power, so it is better to use GPUs because it will do the actual training. However, it could produce a better quality embeddings and a better quality result. So I have pre-run one of the experiments before because it could take some time. Yeah, here it is. So here is the same data set with these 7 columns. And you could see here on the left, while their genetic algorithm is progressing, we could see that it starts with just tabular data features. So it starts with just age, fur length, size, vaccinated, and gender. And then while it progresses, it goes to the images. And so now we see there is a new transformer called image vectorizer. So it is our image transformer, where you could see the name of the architecture. In this case, you could see the exception and also the number of components of the vector of the embedding. And we could see that it could combine multiple architectures altogether. So here we could see exception, DenseNet, for example, and also the features from the tabular data set. So it is the first opportunity, the opportunity of using the image transformer. Another opportunity is to use the image model. So in this case, I could select this chest X-rays dataset. Again, select a column called label in this case. So it is just a binary classification with 2 classes. And in the expert settings, on the main page, we have a new tab called pipeline building recipe. So it allows us to select one of the predefined pipelines. In this case, we select the image model. So it will be our automatic machine learning model for the images that does everything automatically, the hyperparameter search, augmentations, and so on. So you click Save. It will update the preview of the experiment. And you can see now that it will skip the genetic algorithm and go straightly to the final single model called image auto. And it will internally use all their hyperparameter optimization technique insights and run the automatic model. And again, I will show some pre-run experiment. So it is on this X-ray dataset. And it looks exactly similar like other driverless experiments. So you have the iteration data, you have all the rock curves. The only difference is that it's a variable importance. We just have a single feature right now. So it will be just image original transformer that do nothing. So it just do not transform the image path. And we're using just a single image for this automatic image model. And as Dan said, we have here on the right a tab called Insights, where you could look at their, while the experiment is running or once it is finished, you could look at their best individual model so far. So it allows you to see the model hyperparameters, like architecture in this case is IRISnet34, some plots by the epoch, your scorer by epoch on the validation dataset, and also the images themselves. So in this case, we have sample train images with 2 classes, pneumonia and normal. Also have the augmentations that we are applying to the dataset. We have some validation errors where the model sometimes makes errors. So we have true class was normal, but previewed was pneumonia. And also we have these heat maps, the GradCam visualizations, where the neural network was looking at while making one decision or another. And just to give you an idea, so we could work on any domain. So both transformer and image model could work with any images, starting with just simple cat, dog, mouse classification towards different medical images. And just one of the examples could be the dataset from their Zinti platform. So it is a competition dataset where the participants have to predict whether a person wears a mask on the image. And for example, here, so it achieves pretty almost perfect quality. So because the dataset is not really hard, so it achieves almost perfect score. And again, you could go to the insights and see how the metric was progressing, and also see the images, the augmentations, and also the heat maps where the network was looking at while making a decision. Yeah, so that's basically it for the demo.
Great, that was fantastic. Great high-level overview. I hope folks are able to kind of understand what is going on in the product. Based on that, we do have a few questions. We have a little bit of time, so we can take some questions, and then and if you do have questions, now's a great time to go ahead and put them in the question window, and we'll try and get through a few of those in the next few minutes. So Eugene, a couple questions here. It looks like people are wondering, one, how did they get started in kind of computer vision modeling? And you certainly have done this, and you must have started out at some point. So what did you do to get started? And I know tools like this didn't exist then. So, you know, what can students do, for example, to get started in computer vision modeling?
Yeah, it is hard to tell. So there is no single best recipe for this. But like from my point of view, it should be a combination of theoretical knowledge and practical skills. So you have to go through their hard theory and read through some blog posts, papers, books to get their background, the theoretical background. And once you have it, then you just need to go straight away to the real datasets and work with real datasets. For example, in Kaggle competitions or for some pet projects where you could download. So there are lots of data available right now, a lot of tutorials. So you could start with some starting point as a tutorial and then expand it and build whatever you want. So I would say it should be a combination of theoretical knowledge and practical skills.
Yeah, and I think just so people know, if you're in education, you can request a license. We do have an education program. We provide our commercial products to educational institutions, to students and professors to be used as part of coursework. If you want to use this, you can also sign up for a free 21-day trial if you just want to try it out. So either of those options, if you're a student and you're interested in this and you'd like to try it out, I'd recommend looking into those. I am not a data scientist. I don't even pretend to play one at work most of the time, but I can go into this product. It's so easy to use, and build a model, build that pneumonia model with those images with just a few clicks, and let the system really do the heavy lifting for me. So super easy to use. And if you're just getting introduced to computer vision, this is a great way to start, because you can see what the system is doing and how the recipes, for example, that Eugene built into the system from his experience are being used to build the models. So the other question people have is, how do I label the images? And do I have to include a CSV with labels as well, right? So how does that work within the system?
Yeah. So to start the experiment and to start any driverless experiment, you have to have as a label data. So it means that either you're just using tabular data or you're using imaging data. You still have to have the label data sets. So beforehand, before running the experiment, you could start with labeling a small portion of your data. So if you have some images, but they're completely unlabeled, you could just start with a few hundred labeling examples just by yourself manually. Then you could upload this dataset to Driverless and run the model. And once the model is trained, it already have learned something from your dataset, and you could make predictions on the rest of your dataset that was unlabeled. And in this manner, you will obtain some kind of like predictions of the model on the unlabeled data. And from that, you could start, for example, trust the predictions of the model, or you could make another round. So try to correct manually again the labeling of the model and rerun it again. So it could be some kind of active learning approach if you don't have any labeled data. So you could start in this manner, for example.
Great. We talked about GPUs, and so the question comes up. You know, how much would people expect this? How long would it take, for example, to run a model like this? And do we have any idea what kind of resources are needed to build these types of models?
Yes, there is no any restriction on the resources. So if you don't have the GPUs, then you could just use the image transformer that could run successfully on the CPU, and it will be still fast enough because it does not do the real neural networks training. And if you want to try the automatic image model, then you just need to have at least a single GPU, and the rest will be done automatically. So I mean, like it of course depends on the memory of your GPU, the number of GPUs you have, the dataset size. However, there is no any limit. So it just if you have a large dataset and a very small memory GPU, then it will just take, for example, 10 to 20 hours, for example. But if you have 2 GPUs and the dataset is not that huge, then it could take just 1 hour. So there is no any limits.
Yeah, I know I was running the other day on one of our systems, and I think I had access to 4 GPUs, and I was running in, half an hour or something like that with some of these data sets. So yeah, it's going to depend on the resources you have access to. There's a question here just about kind of overall number of images. Is there a general rule of thumb about how many, especially if you're doing classification, for example, how many images you need for each class to make a good model?
Yeah, again, it depends on the complexity of the problem. So I mean, like if you just want to distinguish between cats and dogs, or like different furniture, or just some simple visual stuff, then you could require just about like 100 images per class, and like if you have 10 classes, 1,000 images would be enough. But if you have some medical data and the problem is really complex, then of course it just the sake of the more data you have, the better quality model you will achieve. So it all depends on the problem type and data you have.
Okay, that makes sense. Interesting question about is there any technique that can tell you that images or a set of images can't be modeled, or do you just have to run it and find out? Yeah, probably it is the only way. So it means that you just need to run the model, and if you see that their results afterwards are just completely random, it could mean like 2 things. Either there is some error in data preprocessing, or it is like really a hard data set to model. And in this case, if it is hard data set to model, and you're particularly sure that there is no errors in your data preparation and data post-processing, then the only way to test it out is to label more data and to check where maybe the problem was in the lack of the labeled data. So it could be also the reason why the model is not catching some complex stuff from the training data. Yeah, I think a platform like Driverless AI has a good advantage there, right? Because you can bring your prepared data in, and with the click of a button, you can try it out. And if you get really low accuracy or a lot of false results, you could then go back and kind of look at the reports and figure out, oh, it seems like my data looks bad. Or in that example of cat, dog, mouse, I have a lot of images where the object is relatively small within the image itself, and maybe there's not enough pixels, for example, on some of those images for it really to figure it out. So automation will really help, I think, for people who are in those situations to figure out if their data is good enough before they spend a ton of time maybe tuning a model on their own. And of course, once they use this, they'll realize they don't have to tune those models on their own anymore, right? They can just get started right away with driverless AI. So it should be great.
Yeah,
well,
exactly.
We are out of time,
yeah,
and I just want to thank everybody for joining today. I want to thank Eugene for joining. It's fantastic to have you available to help present and demonstrate and answer questions. And with that, I'm going to wrap things up and turn it back over to Patrick.
Yes, thank you, Dan and Eugene, for taking the time today and doing a great presentation. I'd like to thank everyone who joined us today as well. The presentation slides and the recording will be made available on our Bright Talk channel, and we hope you have a great rest of your day.